Okay, so this is the go at our first video. Basically for this one I'm going to be working through or just talking through the PowerPoint. Feel free to stop, write down the notes. It's a requirement to write down the notes, keep track of them. It's going to be a little bit different. There might be some slides I kind of just skip through because it'd be better if we were actually in class talking about them. This has chapter 12. On Schoology it will tell you the corresponding online chapters from our OpenStax physics book. So, yep, waves and vibrations. It's going to give us a description where I'm going to give you a description of different types of waves and the parts of the waves and that sort of thing. So, an oscillation, when we think about an oscillation, we think about things moving back and forth, back and forth, back and forth. If you ever see an oscillating fan, it goes one way, it comes back the other, just back and forth, and that's what an oscillation is. Guitar strings oscillate, heartbeats, bump, 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 crystals vibrating back and forth, pendulums. And I think you could already tell that we're already getting into waves here when we mentioned guitar strings and pendulums, where they're going back and forth like this, or guitar strings like this. Yep, and lastly here, oscillations can produce waves. So Newton's first law. So an object that's going straight just wants to go straight. To produce an oscillation, there has to be a force applied, right? If the spring's coming this way, a force would have to be applied the other way to push it back. Same thing with the pendulum. Gets to the top, a force pushes it back. Gravity, that is. I'm not going to worry about restoring force at this point. When we have pendulums, they'll slow down. Okay, and if we have guitar strings, we hit them, it's going to stop vibrating. We could have this restoring force, like in this kind of pendulum at a science center. There's probably a little motor at the top that keeps pushing on the cable, causing it to keep its amplitude. So Robert Hooke, we already talked about Hooke's law. Hooke's law deals with forces in springs and the spring constant. You recall this equation right here. We did a little activity where we had a spring and we put some mass on it. It stretched the spring. And in those we actually found the K value. So this negative's kind of weird. Out front it's also kind of big. But anyway, if we recall, let's say we have our spring here and our mass pushes back against it. So I push the mass this way. That'd be the negative direction. So my X would be negative. Negative times negative, positive force. So the spring would be pushing it back in the positive direction. Something we already talked about. What's the maximum acceleration of an object? Maximum acceleration is where there would be the most force. So whenever the spring is compressed or stretched the most, you would have the maximum acceleration. Not necessarily maximum velocity, not at all. Okay? Maximum velocity would occur when it's at its relaxed stage. So here's my spring, I push it back, big force here, pushing it back, most acceleration here, but moving the fastest when it's at the relaxed point of the spring. I'll go through some examples. We already did these, you can look back in another chapter. The reason we bring up Hooke's law is because it deals with this simple harmonic motion. This is kind of an odd definition, because what is a Hooke's law type of force? Okay. It's when the net force is proportional to the displacement in the opposite direction, and in the opposite direction. So basically this, if I, let's say, move the spring back 1 meter, it has a certain force. If I move the spring back 2 meters, it's going to have double the force, okay? And the force is going to be in the opposite direction. Same thing if I were to take a spring and stretch it. Stretch it 1 meter, a certain amount of force. Stretch it 2 meters, double the force. And the force is pushing in the opposite direction. Okay? SHM stands for simple harmonic motion. Typically in class I don't really deal a whole lot with the equations. I'm not going to derive it right now at all. But we could actually determine, based on the energy, the velocity at any point, including the maximum velocity at any point along the the movement of a mass attached to a spring. All right. Well, this is the K value, this is the mass of the spring. This is the maximum amplitude, like how far you pull it back before you let go, or how far you compress it before you let go. And then this is the distance that it's located. So let's say I'm here, I press it all the way back. This would be A. If I want to know the velocity here, this would be X. So where would I get the maximum velocity at? Wherever X equals 0. So X equals 0 when it's back at the relaxed point. Now it'd still be moving, but that's where it's moving the fastest before it starts slowing down to be pulled back. So where X equals 0, you'd have the maximum velocity. That's the question I asked there. A couple more equations here that deal with simple harmonic motion. I'm going to go through them real quick because I just put this on from, I believe it's called something physics. Where is it at? It's from cyberphysics.com, I believe. Like I said, I don't really look at these too much. Sometimes we'll look at the period here. In the last lab where we were circular motion, the period is the time for one rotation. So the period in this case would be the time it takes to go back and forth. Period. Period. It's a time measurement. We think about period as far as like, what's the period of the Earth around the sun? It's 365 days. 365 days for 1 year. The time it takes for one complete cycle. How about for a day on Earth? It's 24 hours. Give you an idea what a period is. All right, now let's get into the actual wave. All right. Typically, when we think of waves, we think of this. Okay. And the wave is simply a motion of a disturbance. So the one thing we got to think about waves is this. It doesn't actually create a movement, in, let's say in this direction, of the fluid or the particles themselves. In a wave like this, they just move up and down. In a wave like sound that moves like this, they move back and forth. But the energy's transferred, but the particles don't actually move the whole way through. So there are some examples, typical ones that we think of. Earthquake waves, there's multiple different kinds. Surface waves, some other ones I don't remember. So mechanical waves, 3 required rules. So the difference, one here too, what's the difference between a mechanical and a non-mechanical wave? An electromagnetic wave like sun, light, the light from sun, anything like that that involves the electric and magnetic fields does not require anything for it to move through besides the electromagnetic fields. The most common one would simply be light, but radio waves, gamma rays, anything like that. I'm trying to think of what else. Radio waves is another big one. But anything that you see on the electromagnetic spectrum where they show that little thing of light that comes out, but they show you microwaves, X-rays, all of those things are not mechanical waves. Right? You have to have something causing the disturbance. You have to have something for it to travel through, like water or air for sound, and then some physical connection between the two. So when we have a wave that goes like this through water, all of those little parts of water are actually touching each other, and that's what we mean by some physical connection. If I have a string and I'm going like this with the string, it's a new thing working out where they have those strings like this, those big ropes. Every part of that rope is connected in some way. Okay, even air touches the other pieces. The other parts of air, the other particles of air will touch each other. Okay, the dust in there, whatever. All right, 2 types of waves. One, transverse. Looks like this. Okay. And secondly, longitudinal. I'm just going to put these up and then I'm actually going to draw a picture. Start labeling parts of the wave. Right here is a lambda. Kind of looks like an upside down Y. I kind of look at like a person running without a body. Like just has legs. One of the cool things about sound, and we'll get to sound later, talking about the different kinds of frequencies, how older people cannot hear as high a frequency as younger people. So the audible range for a human as they get older, and a second guy student taught with showed this with a speaker, it's that students could hear very low pitches or low frequencies and higher pitches than him. It was kind of neat to actually, you couldn't like see it, but they would raise their hand when they could hear it. He was the last one to raise it. They would lower their hands when they couldn't hear anymore. He'd be the first one to lower it. So his audible range for frequencies was much more condensed than the students. At the time I was like 25, I don't know. I was sort of in between. But some students claim that they could hear really high frequencies. So anytime we have a wave, even if it's electromagnetic, you have to have something vibrating. So if you ever see radio towers, people don't listen to radio as much anymore, I don't think, but even within that radio tower, something has to be vibrating, and it tells you right here. I already mentioned period, like a hockey rink, they measure in 3 periods, 3 20-minute periods. And I'm going to go over all this drawing it out. We won't get into that for now. Okay? Well, let's put it up. So I like to talk about sound at a different time, and sound just involves, with me, a lot of different activities, or not really activities, but demonstrations that are kind of neat, which will kind of be hard if we do videos of, because you have to kind of be in here to hear it. But we'll do this example too, or an example like it. Then the last couple things here for now, the law of superposition. I'll also talk about these. What happens when you put the waves on top of each other. One of the cool things about waves, and with sound you really can't tell, because we could hear distinct different voices if everybody's talking in the room, but if the waves come like this and hit each other, they add up, then they go right through each other without actually doing anything. So they come out the other side not looking any different. So this is an example. If we had these two waves striking each other, you would get an increase in amplitude. So when the crest here hits the crest here, it forms a bigger crest. And when a crest here hits a trough here, so they go like this, they cancel out, then they go through the other side. You could look up actually short clips and they'll show like these waves going through each other. So destructive interference. If you notice here, this is a high point, this is a low point, crest and trough. And when they hit each other, they equal nothing. All right. Low point, high point, cancel out, high point, low point, cancel out, low point, high point, cancel out. Destructive. And then constructive, I don't know if it's coming up here. Oh. If you take your fingers and put them in water, it actually makes what's called an interference pattern. But anyway, constructive interference is already up there. It's when you have two high points and they get bigger, or two low points and they get a bigger amplitude. Not worried about this right now. Let's go back here. But an interference pattern is simply the pattern formed by two waves that are striking each other. Right? That's all an interference pattern is. All right. Next I'm going to do the drawings